Well, let's take a look at some solutions and mixtures. Hopefully we'll have more solutions than problems in this one. So solutions are the idea of things dissolved often in water. Doesn't have to be. It could be a lot of other different substances, but predominantly we talk about aqueous solutions. So a concentrated solution means that there's a high amount of stuff dissolved, called solute, in a amount of solvent. Dilute, less solute, things that are dissolved in it than solvent. Now, in order to prepare this is actually a skill that comes up quite a bit on the AP test, is how do you actually make a solution? So if we are using a solid, let's say NaCl, you put this volume in there. Then you put water into what's called a volumetric flask. The volumetric flask has a level at which it will be exactly 1 liter in this case. So the idea is that you put enough water in there, dilute all the solid, then dilute it up into that amount. You might say, well, what's the big deal? Why don't you just mix this with a liter of water? If you do that, your volume is actually going to be higher than 1 liter. And think about it. This takes up space. Even if you break it down to ions, and from our visual standpoint, we think it disappears, it's still there. And so it takes up some space. Additive volumes are not always additive in chemistry. They often aren't. So the best way to describe it is that you have the solid, dissolve it in a less than 1 liter amount of water, mix it up, and then take it to the volumetric flask measuring line, and that'll be your completed amount. So molarity, the unit of solutions about concentration. Number of moles of solute, what's dissolved, in a liter. This idea is what's called concentration. The more concentrated, the higher the molarity. This is used for aqueous solutions. I've never seen it used for anything else. You could possibly use it with gases, but that'd be a stretch. But we use this as another conversion factor like we've been doing anyways. We can also look at diluting samples with a little simple equation. M1V1, molarity in the volume of the first part, molarity volume of the second part. Now, you can go 2 different ways with this, although it's often thought of as diluting. So you go from something more concentrated, you add water, you have a lower molarity but higher volume left over. However, there's the occasion that they talk about increasing the concentration of something, and the way you would do that is getting rid of the water. Evaporation can get rid of it, boiling can get rid of it, but that would make something more concentrated by decreasing the volume, which would decrease the amount of solvent like water, which would increase the total concentration. Again, thinking of concentrated solution, you've got more of the solute in a given volume, dilute less of a solute. So using it as a conversion factor, so, simply putting it through here, you had so many grams of sodium hydroxide, and what you're trying to determine is how many liters of this 1.5 molar sodium hydroxide solution you'd make. Again, we need to get in a ratio of grams to moles. So that is grams to moles and moles to liters, because this is going to be 1.5 liters. This will tell me my volume. All of these conversions cancel out. Again, you start off with your sig figs of your starting value, which is why you're going to have 256.3 milliliters or 0.2563 liters of this 1.5 molar NaOH. And see how it needs to be labeled out. Don't forget your units, folks. Don't forget your labeling. It's all very needed in order to get all your points. Diluting, quite the same. List off your variables. You want to list these off so you kind of organize them. And one of the things is that you want to keep your volumes constant. It doesn't have to be in liters. Molarity is always going to be the same. There is no other concentration factor that we would use. But it could be milliliters, microliters, kiloliters, liters, as long as they're the same. You go through, substitute in, right? We see my molarities are going to cancel. I was like trying to set that up. Not needed for AP, but I'm taking this back from an honors chem level. And determining your amount of milliliters needed. Sig figs based upon your numbers that you were given, 2 sig figs, which is why you need 140 milliliters of this 3.6 molar hydrochloric acid. So, couple examples with solutions, of course. amount of grams to make a solution. Very common. You need an amount, you need a volume. You take the liters, this is the molarity, 7.89 moles per liter. So my liters are going to cancel, and my molar masses is going to change this moles to grams. 2 sig figs, because that's what I started with, which is why it's 2,800. Another common area, volume of this when I need so many grams. So kind of the reverse. Need to change my grams to moles. This is my molarity, and you might notice, hey, you have 0.5 moles on the bottom. Yeah, I can do that. This is a conversion factor. It's just a ratio. Ratios can be flip-flop any which way. That's the magic of conversions. Again, multiply everything across the top, divide by these individually. If you're not getting this answer on your calculator, you're doing it wrong. I can show you exactly what you should do to always get the correct value here. Ions in solution. So often we'll look at going forward in this course is that compounds, when they dissolve, are going to make multiple ions in solution. This happens with acids and bases. It also will happen with net ionic equations and things like that in the next unit. So we want to make sure we are aware of how many ions are present. So if I wanted to have 2.3 liters of this molarity of bromine in solution, because maybe that's part of my reaction, what volume of this iron 3 bromide would I need? So you want to take seeing how much does each of this deliver considering bromine. So I take the moles per liter, right, the molarity. I'm converting the iron 3 bromide into how many bromine ions it will have, and that'll be 3 moles. So that'll be 0.369, and it's still over 1 liter, so that's my molarity. Now I want to see if I have my volume of my concentration of bromine, how much volume of this 0.369 iron 3 bromide would I need? Dividing it by both sides, this will give me my volume. That I'd need 2.2 liters of the actual iron 3 bromide to get 2.2 liters of my 0.369 bromine ion. Either of these, you could talk about it as the same, but I'm just trying to illustrate the idea that I'm not making a bromine ion solution. I'm using iron 3 bromide as my source of bromine ions. So keep that in mind as you go through this. Last one. What mass of this is needed to make 0.56 liters of a certain concentration of chlorine ions? This one's a little more straightforward. So I know I'm going to need 0.56. Here's my molarity. That'll tell me my number of moles of chlorine ions. For every 3 moles of this, I need 1 moles of that. 1 mole of this is so many grams. Therefore, do my math. My significant figures, I started off with 2 sig figs. I end with 2 sig figs with a 3.8 grams of chromium 3 chloride. Come in with your kinds of questions, and I hope to talk to you later. Take care.